Welcome back to derivability now. Okay, here we're going to take a look at the equations of motion for rigid bodies in the plane. Okay, before we jump into the big part, I want to just remind you that for rectilinear motion, Newton's second law, net force equals ma, describes the motion of the object's center of mass, no matter what else is true. That is, sum of forces equals m times the acceleration of the center of mass g with respect to some outside fixed origin O. Okay. Otherwise, we're going to be taking a look at where the meat and the potatoes are, you might say, starting with this kinematics formula that I derived in a previous video on the general plane motion of a rigid body. Go check that out on the channel if you want to see how that's derived. Otherwise, it might look familiar to you, or you may just want to accept that for now. Okay. To start with, let's see if we can figure out the force on some little mass element in this rigid body. Okay, I'm calling it m sub I. Now later we're going to suppose that that is infinitesimal, so that's going to become dm later. All right, but for now I'll just call it m sub I, and I can label its position as r sub io relative to the fixed origin O, or r sub ip relative to some point p in the rigid body. Okay, in fact it doesn't have to be in the rigid body, but in my picture it is. And then of course we need to know the position r sub po of p relative to O. Okay, now right now, other than Newton's second law, the centroid g is not playing a role just yet. All right, so first let's write down a formula for the force on this mass element. Well, that's going to be the mass, m sub I, times acceleration, sub io. All right, so there's that equation. Okay, now because we're interested in rotations, we want to take the moment of this force, say about p. Okay, that is the torque of that force about p. So we need to take the cross product r sub ip crossed into f sub I. Okay, so here you can see how I've applied that cross product r sub ip crossed into each of the three terms on the right hand side. Okay, now let's resolve these. There's two of them that are going to be able to simplify, two out of those three. Okay, well first, okay, m and omega are scalars. So here I'm essentially taking r cross r, that is r sub ip cross r sub ip. Okay, so any vector crossed into itself is going to give us 0. Okay, so this term just drops out. All right, next, what I've got here, with the exception of m, in this term, is I've got an r cross alpha cross r. Okay, I'm leaving the subscripting off for just a moment. Okay, now this triple cross product can be resolved using the back cab rule. Okay, and that gets rid of the cross products, and what that gives us now is alpha times the dot product r dot r, and then minus r times the dot product r dot alpha. Okay, now for planar rotations, alpha is a vector that points out of the board, out of the screen, or into. R is a vector into the screen. Okay, so this dot product is equal to 0. All right, so all that's left in this first triple cross product, you might say, is just alpha times the scalar r squared. Okay, so let's rewrite that now. Okay, so over here in the bottom left, what I have is the current state of affairs for our formula. Okay, the moment of all the forces acting at point I about P. Okay, we have alpha, and then m sub I times r sub ip squared plus m sub I r sub ip cross a sub po. Okay, now at this stage, what we would like to do is take the sum of the moments that could be acting over the whole rigid body. Okay, over all possible points I. Okay, and on the right-hand side, we're basically going to turn our m sub I terms into dm terms and integrate. Okay, so let's do that next. All right, what we have next is the sum of the moments about P equals alpha times the integral of r sub ip squared dm sub I plus the integral of r sub ip dm, and then that integral, which is a vector, cross a sub po. Now, alpha can be brought outside the first integral because it's a constant with respect to the dm integration. It's a constant. It's the same thing for every point on the rigid body. Likewise, a sub po can be brought outside of that second integration. Now I have to bring that out on the right side to respect the order of the cross product. All right, but otherwise, after we do the integration, which turns out to be a vector, then we can take the appropriate cross product. Now, each of these integrals is fairly straightforward to recognize. Okay, this integral of r squared dm is really the moment of inertia of the rigid body about point P, because we're measuring point I from point P, and then we're integrating all such mass elements, dm sub I. Okay. All right, now the right-hand side, the integral on the right, okay, this takes a little bit more thinking or looking into things. This is actually the mass of the object, the total mass of the object, times the coordinate of the centroid G measured relative to P. Okay, now if there's any doubt about that, just write down r sub ip in terms of like an x component and a y component. Look up your definitions for the coordinates of a centroid in terms of an integral, and I think you'll see that. So next, let's just rewrite our equation containing these new results. Okay, well, at least for now, things are starting to look like it's coming together, a little simpler. All right, so sum of moments about P equals I sub P times alpha plus R sub GP cross, I've written it in parentheses, kind of in a suggestive way, M times A sub PO. Okay, now this might look very helpful, but it's not that helpful. Okay, whenever you see the M times the A together, well, M times A kind of makes you think of net force, but it's not the right point. Okay, the correct point for M times A is the centroid, okay, not point P. So what we have to do next is we have to use another version of some kinematics to turn this acceleration PO into acceleration GO, and there'll be some other adjustments that go along with that. Okay, so let me remind you of the kinematic equation. It'll look similar to the one we used at the beginning that we're going to use to fix that. Okay, so this kinematic formula, the general format, should look familiar, and I've made some adjustments on the subscripting, but what we're going to do ultimately is we're going to substitute for acceleration PO into this cross product where we have R GP cross into that. Okay, so let's see how that turns out right now. Okay, all right, so what we've done here is we've substituted in place of A sub PO, this whole thing, okay, so R sub GP across all of these terms. Now we're going to get some similar things happening that we did earlier in our discussion. First, let's just remark here that two position vectors, or really any vectors, that have reversed subscripts on them are negatives of each other. Okay, so we'll need that in a minute. Now, regardless of that part, here I have a cross product of two vectors that are essentially in the same direction. So I'm going to get that combination equaling 0. That's just going to go away. Okay. Now, this first grouping here, let me rewrite it this way. Let me rewrite it as R sub GP cross alpha cross, and then instead of PG, I'm going to write R sub GP. Now, I'll need a negative on that because I've reversed the ordering of those subscripts. Okay, but otherwise, we get to use our back cab rule on this again, like we did a little while ago on the first screen. So this is going to be the minus, and then alpha, and then R sub GP squared. Now at that point, it doesn't matter if it's PG or GP. It's a magnitude squared. Okay, this last term stays the same. So now let's substitute back into the sum of moments equation. Okay, so here we are substituting what we got on that last screen. Okay, after having taken the cross product. Okay. All right, now we can do a little bit of rearranging. And we are just very nearly there. Okay. Sum of moments about P equals. Okay, now after I distribute the M through to this term, I'm going to have an I sub P term and some other things that both contain a common factor of alpha. So let me factor those out. Okay, and then otherwise, let me group my M with the A sub GO in this cross product here, R sub GP cross M times A sub GO. All right, now let's identify a few things here. At the end, now I really do have M times A sub GO. This is the net force. Okay, so it's an M times A like it was before, but this time it's the right A times M. Okay, now this might look a little backwards, but using our parallel axis theorem, this is really equal to I sub G. Okay, so finally, we get the sum of moments about P, any point P we like, equals I sub G times alpha, plus this last term, R sub GP cross the net force, M times A sub GO. Okay, this last term represents the moment of the net force about some point P. All right, now this, I'll put it in a box because this is the result we were looking for. Okay, this is the most general equation you can have for the sum of moments of a rigid body executing motion in a plane. Now, there are a couple of special cases which I'll talk about next. Okay, there are a couple of special cases I'll go through fairly quickly here. So the first one, if the point in question, P, just happens to be the centroid, then you get a very simple looking formula. Sum of moments about G equals I sub G times alpha. Okay, what happens is the R sub GP term that you would otherwise have in that boxed formula from a minute ago. R sub GG is just 0. It's the centroid measured from the centroid. Okay, so this might be the simplest version, and it's fully applicable. It's fully general. Although there are times it's just not necessary. It's not convenient to calculate the sum of moments about the centroid. Okay. So that's why we have the other more general equation. Okay. All right, next, P could be a fixed point. That is a fixed axis of rotation. Well, in that case, we have sum of moments about P equals I sub P times alpha. Okay, now there are some details that I left out there, but basically there's the only acceleration of GO is tangential. Okay, and we can end up using the parallel axis theorem again to combine those two terms into an I sub P. Okay, now the third one is that if you have a very special case with rolling motion where the centroid is always in the same position relative to the instantaneous center. Okay, well then you just get the same sort of equation we did in number 2, except your fixed axis of rotation now becomes the instantaneous center. Okay, and then finally, maybe you don't have any angular acceleration at all. Now, you could still have an angular velocity that's not 0, but as long as it's constant. And you still could have rectilinear motion. Okay, so in this case, you have one of two things. You have the sum of the moments about G equaling 0. Okay, I'll box some of these others in here as well. They're important. Okay, the sum of moments about G equaling 0. Okay, and we get that from special case number 1. Or if you go back to the most general version of the equation, sum of moments about some other point, well, the alpha term goes away, and then what you're left with is R sub GP cross the net force. Okay. All right, so of course the moment consideration took us a lot more time to figure out, to understand, than just the net force for the rectilinear motion. Okay, some of this has been a little condensed because I didn't want the video to run too long. But this gets you where we need to be to start analyzing various problems for general plane motion. Okay, well, hope this has been helpful. Give me a like and subscribe. Share this channel with your friends who are interested in for this video, something like mechanical engineering, but just generally things that are otherwise on the channel. Appreciate you sticking around here, and we'll see you next time.